Okay, let's wait one more minute and then we start. Okay, let's see. Oh, sorry, I lost. Yeah. So good afternoon, everyone. Welcome to this second lecture of the mini school on open quantum systems, or introduction to the theory of open quantum system. Like last week, our speaker is Dr. Graeme Pleasance from UKZN. He's a postdoc, a NITheP postdoc at UKZN. And with us on the panel, as usual, is Dr. Sinaisky, who will moderate the answer and question session after the presentation. And of course, if there are urgent questions, please put them during the talk. This should have a school character and not so much a lecture character. Please make use of the Q&A facility to ask the questions, and Ilya, as I said, will moderate the questions. Graeme, it was very nice last week to review the foundations of the theory of open quantum system, and today Graeme will share probably the interesting, the beginning of the interesting parts. Yeah. So Graeme, please welcome to share your screen, and we are really looking forward to your second lecture.
Okay. Can you see my screen?
Perfect. Yeah, fantastic.
Okay. Well, thank you, Francesco. And yes, welcome back to the second lecture on of this mini school series on an introduction to open quantum systems. So yeah, let's just get straight back into things. So in last week's lecture, I basically gave an overview of the statistical foundations of quantum mechanics. So it was more or less a kind of textbook overview of things. And in this week's lecture, what I'll do is apply some of the ideas and concepts that I talked about last time to kind of provide you with some of the key ideas and concepts in the theory of open quantum systems. So in this way, let me begin by just reviewing some of the key things that I introduced last time that will be important for today's lecture. So yes, I introduced the concept of a density matrix as essentially a way of essentially as a way of completely characterizing the statistics of the state of a quantum system. And in particular, there are kind of two categorizations of a density matrix as either yeah.
Are we supposed to see now not your introduction to open quantum system slide? Have you switched the slide? Yeah, because at least I see the front slide.
Okay. Sorry, let me stop sharing then. Okay, I think that might. So I think my sharing was paused. So I think it was paused on the first screen for some reason. Can you see me change the slides now, or is it still stuck on the first screen?
No, it's the first screen for me. If any other participants see something different, they can tell me.
Yeah. Graeme, are you sharing your desktop or are you sharing Keynote?
I thought I was sharing Keynote. Okay, wait, let me just stop sharing for a second and then let me try to restart it.
Maybe something went wrong.
Okay.
Yeah.
Okay, you still can't Yeah, for some reason, when I enlarge it, it says it's pausing the sharing. For some reason, I don't know why. You can see my screen now, and you can see me change the slides, right?
Yeah, but we see your keynote like inside keynote.
Yeah. Okay, but it will do the trick. Yeah.
Okay, wait, just sorry about this. If for some reason when I do the full screen, it says my sharing's paused. So for some reason it gets stuck. Okay, sorry about this.
Okay, but maybe you can just take away this plateau with documents and audio, which is to your right. At least for us, it's right.
No. Yeah,
I would suggest let's use this system and let's change the slides here, and it will do the trick.
I can try restarting Keynote if that will work as well. Wait.
Let's do the last attempt. Yeah.
Okay, let me, sorry. So yeah, sorry about this again. We just tested this like 5 minutes ago and it worked, so I don't know what's going on now.
Somebody suggested maybe share screen after presenting. Maybe first start to present and afterwards do the share screen. At least try.
Okay, yeah, that might work. Okay, let me just get this back up again. Okay, let me try sharing my screen again. Is it working now?
Yeah, it's
okay.
Yeah.
Okay, good. Finally. Okay. Okay, sorry, yes. Okay, yeah, I would. So when I was talking about period mixed states, I was talking about this slide. So, okay, yeah. So last time I basically mentioned that, or I introduced the concept of a density matrix as a way of completely characterizing the statistics of the state of a quantum system. And in particular, there are two categorizations of density matrix. So namely as either pure states or mixed states. So if we have a isolated quantum system whose state is the corresponding density matrix of this system can be written as a pure state, which is given at the top of this slide. So the outer product of psi with itself. However, there are more kind of general ways of constructing a density matrix of a quantum system, so more general types of states. And weighted or with coefficients given by the weights W alpha. And these weights W alpha are normalized to unity in the sense that their sum, so the sum of W alpha overall alpha is equal to 1. In this way, you can kind of interpret these weights as corresponding to kind of classical probabilities. And yeah, intuitively, you can kind of think of so for a quantum system which is whose density matrix is a mixed state, so in the form that's given on this slide, you can think of a quantum system as being in a mixed state as reflecting there being some classical uncertainty or randomness in the preparation of the state, where these weights basically give you the probability of your quantum system being in a particular pure state, psi alpha. Okay, and you can kind of introduce a measure of purity. So this trace of rho squared is for a pure state is, or if rho is written as a pure state, then the trace of rho squared is equal to 1, and if it's in a mixed state, then this quantity is always less than 1. And in general, the trace of a density matrix is always 1, since this just follows from normalization of probability, essentially. Okay, so I also, towards the end of last week's lecture, I talked about composite systems. So composite systems are quantum systems whose state space has the following tensor product structure. So what's written on this slide is H1 tensor product H2, and an operator, so any operator or observable acting on the combined Hilbert space H, can in general be written as a linear combination of the tensor product of operators defined on each of the respective subsystems. So what's given on the right side of the slide. And one important point to make is that if, say, for example, that we're only interested in characterizing the state of one of the subsystems, so we're given the state of the entire composite system, but we only want to focus on what's going on in one of the subsystems, then what we can do is we can apply this so-called partial trace operation to obtain the reduced density matrix of one of the subsystems. So on this slide, you can see it says rho 1 is equal to the partial trace over the second subsystem, or the trace of rho over the second subsystem. So this object that's obtained through the partial trace is called the reduced density matrix. And formally, it basically gives you a complete characterization of the statistics of that subsystem. And you can think of like the partial trace operation as what you're kind of doing is you're constructing the state of the entire composite system. And then what you're doing is, when you take the partial trace, is kind of throwing away any information you have on one of the systems just to obtain the reduced density matrix of in this case, the first subsystem. Okay, and in the special case that the density matrix of your composite system can be written in the form at the bottom, so as the tensor product of the respective reduced density matrices, then rho is said to be, each of these two subsystems are said to be uncorrelated. Okay. So yes, in today's lecture, we're going to now talk about, or we'll get into the kind of the main theory of open quantum systems. So on this slide, I've listed a brief outline of some of the things that I'll talk about. So I'll begin by just kind of introducing the kind of the ingredients that we need to really talk about open quantum systems. And then I'll talk about ways in which we can simplify the kind of general description to a more simpler description of open quantum systems using the concept of a dynamical map. So when we introduce dynamical maps, what we can then do is introduce the idea of a quantum Markov process. And what I'll then go on to do is talk about Markovian quantum, or the derivation of a Markovian quantum, or I should say the construction of a Markovian quantum master equation. And then in the last parts of this lecture, hopefully if we get onto it, I'll go through a microscopic derivation of the Markovian quantum master equation. And and then if I have enough time, I'll talk about some physical examples. So hopefully I'll be able to get through most of this in today's lecture, but yeah, we'll see how it goes. I might have to defer some of the material to next week's lecture, but yeah. Okay, so in this slide, there's this, I've just listed a kind of roadmap of some of the kind of ideas and how they're kind of related. So what we're going to do in today's lecture is kind of focus on what's on the left bottom corner of this kind of roadmap. So where it says, we'll consider with a kind of general microscopic theory, then we'll go into the reduced dynamics as described through the dynamical map, so going to the left. And then we'll go down where it says Markov, we'll then talk about the kind of formulation of quantum Markov processes in terms of the dynamical map, in particular introducing the idea of introducing a Markovian quantum master equation as a master equation in so-called GKSL form. But I'll talk about more of this throughout the lecture. Okay, so last time I kind of gave you a kind of very brief definition of what an open quantum system is. So I said that an open quantum system is a quantum system that interacts with somehow with an environment. So how do we kind of, in the most general case, model this type of system? So the way that we can do that is by thinking of composite systems. So if we have a quantum system interacting with an environment, so its surrounding environment, then we can represent one of these subsystems in a composite system as our quantum system of interest, which we can label S, and the other subsystem in our composite system we can label as our environment, which we can label as B. So in total, we have a composite system which is given by S plus B, which schematically is depicted on the right of this slide. So so our quantum system of interest S, the state of this system is characterized by the reduced density matrix rho S, and similarly our environment B, its state is characterized by this reduced density matrix rho B. And in this kind of general formalism, what we're assuming is that that we can kind of partition our total system in this way, and there'll be some general interaction between these two in our composite space. There'll be in general some interaction between our system S and our environment B. So how can we describe that interaction? Well, in the kind of very broad sense, when we talk about open quantum systems, what we're interested in modeling is how the reduced density operator rho S, or how the time-dependent behavior of this reduced density operator is influenced by our system interacting with this environment B. Or in other words, what we want to do is we want to give a dynamical description or derive an equation, a general equation of motion for this reduced density operator rho S. So the starting point, well, we know that I talked about last time that the dynamics of a closed system, isolated system, can be described through the time-dependent Schrödinger equation. And a key ingredient in the time-dependent Schrödinger equation is the Hamiltonian. So for this general, so for our total system, so for open system S plus the environment B, we can write down effectively the time-dependent Schrödinger equation for this total system. So we start with defining the Hamiltonian of our total system, which is given as H at the top of this slide, and just using what I talked about at the beginning of the lecture, that we can write any operator on this combined space as a sum of the tensor products of operators pertaining to each of the subsystems. We can write a general Hamiltonian of our open system plus environment in the following way. So where in this case here HS is the Hamiltonian of our open system, HB is the Hamiltonian of our environment, and HI denotes some interaction between the two. So it's worth noting that the HS and HB only act on the subsystems S and B respectively, whereas this interaction Hamiltonian belongs to kind of the joint composite space, since it describes some form of coupling or interaction. And just as a kind of shorthand, you can write this as we can drop these. So these IS and IBs are just the identity operators on each of the subsystems. So the reason that you need to include these formally is because you need them to give the correct dimensionality of the total Hamiltonian. But in general, when you read papers or books or anything, people just usually write it in the form that's given by the second equality, because these identity operators don't have any effect in the dynamics. So so that's just how you can write the general Hamiltonian of our total system. And what we can do then to describe the dynamics is to write down the density matrix of our total system. So in the most general case, this will be a mixed state. And because we're talking about its time evolution, we can write down a density matrix rho at time, let's say t equals to 0, as just, you know, what I've showed before as the sum, or as a sum over a set of pure states with weights W alpha. So in order to evolve this state in time, what we do is we just apply like a unitary time evolution, as we do for any closed system. So for a density matrix, the way you get the time evolution is by acting the unitary time evolution operator on the left-hand side, and then it's a joint on the right-hand side. So by doing this, you can then write rho in the following way that I've given on the right-hand side of the equality. And if you just take you can then set up a differential equation for rho by just taking the time derivative of both sides, and using the fact that the time evolution operator u can be written as e to the minus I, the Hamiltonian h multiplied by t, you can then show that the general equation of motion of this density operator of our total system is given or in the middle or at the bottom of the slide. So this equation of motion is what's called the von Neumann equation, but really it's just kind of the Schrodinger equation, but also not just applying to pure states, but also applying to mixed states. Okay, and because we only care about, well, I should say that so what we want to look at is, or what we want to model is the dynamics of our reduced system S. So in this way, we can take the partial trace over both sides of this dynamical equation. So we can then set up an equation of motion for just the reduced density operator of our open system rho s. So you can do that by just just using the partial trace operation that I described above. And by doing so, we can then write down a general equation of motion given in the bottom right for our reduced density matrix rho s. So this gives us, okay, we've been just kind of starting in this kind of this general picture. We're able, for any open system interacting with some environment, we're able to write down an equation of motion for the reduced density matrix of our system. So you could think, okay, this is fine. You know, this gives us a good description, and we can just apply this wherever we want. But the crucial thing to kind of understand here is that in general, when we think of open systems interacting with environments, generally, well, the environment can be in principle anything, but in general, we model the environment as a macroscopic system. So when I say a macroscopic system, I mean a system which contains an infinite number of degrees of freedom. So we assume that our environment is much larger than our open system. And in that way, if we want to describe the dynamics of our combined system and environment, we can kind of tell this will be very complicated, because if you look at the von Neumann equation, what this equation of motion contains essentially is it contains information relating to our open system, but how it essentially couples to every single degree of freedom in the environment. And because I said the environment is generally taken to be very large, what we have to do is, if we want to basically solve this equation of motion, we have to end up solving a very large system of equations of motion, which is usually intractable to do. So even in the case where we take the partial trace of this equation of motion just to get rho s, this resulting equation of motion is usually just as complicated to describe. So at this point, even though we've kind of managed to come up with a general formalism, it's not particularly useful at this point, because it's usually too intractable to give any kind of practical description of any system, or any like physical system that we want to model as an open system. So the kind of question is, how do we kind of proceed to kind of simplify the description in a way that gives us a kind of good model that isn't too complicated or too simple, sorry, but gives us a kind of accurate description of some open systems. So the kind of starting point to kind of simplify the formalism is to introduce the concept of a so-called dynamical map. So suppose that we have a system environment, so S plus B, that is, or the state of our system, the total state of our system plus environment. Suppose this is initially prepared in an uncorrelated state. So our total state rho is given by rho S tensor product with rho B. Then the transformation describing the transformation of between the reduced density matrix rho S at time t equals 0 to a later time t can be written in the following way. So what's given at the top of this slide. So what we're doing is we're just evolving the state of our total system S plus B according to a unit, in a standard unitary way, and then we're taking the partial trace over the environment B to get rho S. And so in order to evaluate this partial trace explicitly, what we can do is we can write the initial state of our environment rho B according to its spectral decomposition. So this is something that I talked about in the last lecture. So you can write rho B as well, you can write rho, if we basically introduce an orthonormal basis for our environment B, then rho B can be written in the following way, where lambda alpha are just the eigenvalues of this density this density matrix. Then just plugging this into the equation at the top, you can basically construct this so-called dynamical map acting on our open system. So basically the dynamical map is written as V of t acting on rho S, and you can write it in the way that's given in this blue box. And so you can see importantly that on the right hand, so where I've written V of t rho S, on the right hand side of this equation, you can see that everything on the right hand side belongs to or only acts on the Hilbert space of our open system S. So you can see that in the following way. So below you can see that I've defined this operator called W, and in the following way. So it's just given as so we have our unitary time evolution operator, and then we're sandwiching it between these states phi alpha and phi beta, which belong to our environment B. And because we're sandwiching it between these two states, you can basically tell that this operator will only act on our open system. So basically, we're not taking the partial trace, but we're kind of removing any dependence in this expression on our environment. And these operators W satisfy so they satisfy this sum that I've given. So W dagger. So the sum of W alpha beta dagger multiplied by W alpha beta is equal to the identity. And in this way, so this quantity that I've defined as the dynamical map V of t, you can kind of just from these expressions, you can see in general is defined as a linear map, which maps is defined as a linear map from the set of physical states of our open system S onto itself. So basically, if we take a reduced matrix and we apply the dynamical map to our reduced matrix, reduced density matrix, if we apply our dynamical map to this reduced density matrix, then we basically evolve it from some initial time to some later time t. And you can see from the properties of this operator W that if we take the trace of V acting on rho S, you can basically show that using the cyclic property of the trace, that this is just equal to the trace of our reduced density matrix at times t equals 0, which is by construction is equal to 1. So basically, when we evolve a state under this dynamical map, it preserves the trace of our density, of our reduced density matrix. Okay, so, okay, this is just a kind of small kind of caveat that I put here. So, so when we in general talk about the different types of operations that we can, so okay, let me introduce it in the following way. So, I've mentioned that the dynamical map, what it does is it maps some density, reduced density matrix at times t equal to 0 to another density matrix at time, a reduced density matrix of our open system at some later time t. So you can think of this as kind of representing some type of quantum operation on our open system S. So in a kind of more general sense, we can any kind of operation that you can perform on a quantum system can be described in terms of what's called a quantum channel. So a quantum channel, in a similar way, is basically a linear map which maps from the space of physical states of your system onto itself. So basically, when you apply a quantum channel to a density matrix, it takes this density matrix and maps it to another density matrix. And in the general formulation of quantum channels, what you require is that this map is what's called completely positive and trace preserving. So I won't go into the specific details of this, but you basically require your map to be completely positive and trace preserving to ensure that your channel is mapping density matrix onto density matrix. Because you could consider a type of operation which maps a density matrix onto something which isn't a density matrix, which is problematic because, well, you're ending up with an object that doesn't have a physical interpretation, or it doesn't give you a physical description of your system. So you have to kind of be careful in the way that you can construct operations on systems. So in the bottom of this slide, I've written, okay, so on the bottom of this slide, I've written an expression for a quantum channel, which is which I've written as this linear map phi subscript m acting on a density matrix rho. And in order for this channel to be completely positive and trace preserving, it has to emit a so-called Krauss decomposition. So the Krauss decomposition is just given by the right hand, what's on the right hand side of this equality. So a Krauss decomposition. So if a quantum channel emits a Krauss decomposition, then you can write it as this linear sum involving these operators sigma, what I called, sorry, not sigma, omega mk. So these omega are positive operators acting on whatever system this row is describing, and the sum. So I haven't actually written it here, but there's the sum of omega dagger omega is equal to the identity. Okay, so basically, the way that we can apply this kind of the way that we can kind of apply what I talk about to the dynamical map is that, well, we also require our map. We also require our dynamical map to be completely positive and trace preserving, right? Because if we want to evolve the reduced density matrix of an open system, we have to be evolving our state, or we have to be evolving rho s to some later to another state at some later time, and this state at a later time also has to be a density matrix. So in that sense, our dynamical map has to admit a Krauss decomposition, and you can see that what's given in this blue box and some of the properties of these operators W, that this does in fact in general admit a Krauss decomposition. So by construction, a dynamical map with the assumption that we have an initially uncorrelated system and environment is completely positive and trace preserving. Okay, I just saw a question pop up, so I don't know if it's worth.
Yes, kind of the person is asking about the definition of the Krauss decomposition. Can you please repeat it?
Okay. So yeah, if we have a so any linear map, or any map phi which transforms a density operator rho to a or I should say any linear map which transforms a density matrix rho from a set of full density density matrices onto another density matrix has to be what I said is completely positive and trace preserving. And basically, there's a theorem which was given by Krauss, which tells us that in order for a quantum channel or this map to satisfy this property, that it maps density matrices onto density matrices, is that it has to. So basically, the necessary and sufficient conditions for this to be true is that it has to have a Krauss decomposition. So the Krauss decomposition is just given by this equation at the bottom. So if we have a quantum, okay, when I say quantum operation, you can think of anything. This operation can describe anything. So, so say for example that this operation describes like a measurement, where when we perform this operation, we return a measurement outcome, what we label M. Then what this tells us is that this measurement operation has to, according to this theorem, it has to emit a Krauss decomposition, which is given at the bottom. So it has to be given as this sum over these operators, which I labeled omega. So these operators are they're I think they're positive operators just acting on the space of our system, whatever state space rho is defined. And so I'm not sure if this is addressing the person's question specifically, or they wanted me to talk about something specific, in particular regarding the Krauss decomposition. Or
I think that is fine, and I think you can continue.
Okay, sure. Yeah, I think all you need to know is that if you want your quantum channel to be if you want your quantum channel, or you want to just to describe an operation which is completely positive and trace preserving, it has to be written in this form. That's the kind of synopsis. Okay, so so basically the reason I wanted to talk about this briefly was because that by construction, this dynamical map that I've introduced V is completely positive and trace preserving. So it maps a reduced density matrix at times t equal to 0 to another reduced density matrix at time t. Okay, so so here I've just given, I've provided a commutative diagram that basically.
Sorry, Graeme. Can you please clarify one more aspect? In very simple terms, how are Krauss operators different from other operators? I think maybe you missed the normalization statement.
Oh yeah, sorry. I think I mentioned that only very briefly. So yeah, I'll elucidate on that. So these operators omega these operators omega, they have to satisfy the normalization that the sum of these so the sum over the two indices km of omega dagger omega has to be the identity operator. So they basically have to fulfill this. They have to fulfill this kind of normalization condition. So that's how these Krauss operators are defined.
Okay, thank you.
Okay, yeah. Okay, so so here I've just given a commutative, or this just illustrates a commutative diagram showing how you can evolve the or how you can obtain the reduced density matrix of our open system at some time t. So you can either, or starting from assuming the density matrix of our combined system and environment is initially uncorrelated, then what we can do is we can evolve it according to a unitary evolution. So, you know, just a kind of standard unitary time evolution up to some time t. And then at this point, we can take the partial trace to obtain rho s at time t in terms of the, at times t in terms of this dynamical map. Or equivalently, what we can do is we can take the, at times t equals to 0, we can take the partial trace over our environment just to get rho s at times at the initial time, and then apply just the dynamical map v of t on rho s to then obtain our reduced density matrix at time t. So basically, what this just shows is that these two kind of paths are equivalent. Okay, so yeah. So after introducing this idea of the dynamical map, we can use the dynamical map as a kind of starting point to kind of simplify the analysis of open quantum systems. So in the kind of, from what I was talking about previously, this dynamical map, it basically gives you, it describes a very general time evolution. So what we can do is we can now introduce the idea of, as a way of simplifying a general evolution, we can introduce the idea of a so-called dynamical semigroup. So a dynamical map can be written as or defines a dynamical semigroup if it satisfies the following property that's given at the bottom of the slide. So in this blue box. So if we have 2 times t1 and t2, then if our dynamical map satisfies this kind of composition property, then it defines what's called a dynamical semigroup. And what's important about dynamical semigroups is that they can be shown to basically describe or characterize quantum Markov processes. So, okay, this is what I can now go on to talk about. I think there was another question that popped up, so should I answer that as well?
Yeah. For this to work, is it necessary to assume that there are no initial correlations in the composite system?
Yes. So that point's very important, that you need to, in order to define a dynamical map which is completely positive and trace preserving, you need to assume initially uncorrelated system and environment. So that's kind of crucial to this derivation. So you can look at more general like systems where you don't have a initially uncorrelated system and environment. But what happens is that the dynamical map that you introduce via this formalism on this slide is that by construction, it won't always be completely positive and trace preserving. So what happens is that you can potentially, you can map, what this dynamical map will do, will potentially map density matrices onto things that aren't density matrices, which is obviously problematic, because then that kind of gives you an unphysical description of the state of your system at some later time. So yeah, so this initial condition is important. Okay. Yeah, so I basically, so I just introduced so for a dynamical map which satisfies the properties at the bottom, in the blue box at the bottom, then it defines what's called a dynamical semigroup. And dynamical semigroups are connected to quantum Markov processes. So let's now talk about that. So we can, from introducing the definition of a dynamical semigroup, we can introduce a operator, or a new operator, what we call L, or calligraphic L, as an operator, we can introduce it as the so-called generator of a dynamical semigroup, in the sense that we can write the dynamical map as V V is equal to the exponential of this operator L multiplied by T. So you can see that this representation of our dynamical map will, by construction, satisfy the dynamical semigroup property, since, well, so let me just go back to this next slide. So if you just look at this dynamical semigroup definition, you can kind of intuitively tell that, well, our dynamical map, if we have a dynamical map that satisfies these properties, then we can expect it to have an exponential form, since, you know, a general property, if you multiply two exponentials together, their exponents add. So you can see that with this definition of the dynamical map. So when we introduce the generator of this dynamical map, when we introduce the this form of the dynamical map, we can see that it, by construction, satisfies this semigroup condition. Okay, so by taking, from the property that the reduced density operator or reduced density matrix rho S at some later time t is obtained by evolving our initial, the reduced density matrix of our initial system, of our initial rho S through, so we obtain rho S of t by acting our dynamical map on the initial reduced density operator of our open system. So then, if we,
Can I ask you one more question? So, because there is one more question. So for this to work, calligraphic L must commute with its earlier and later selves, right?
Well, it's time independent. So yes. So you can, yes, with this definition of the, with this representation of the dynamical map, you can see that if you write, you know, if you basically just substitute two different times into this expression and then multiply or compose the dynamical map at some time t1 plus t2, you can see that this will just be in the same form of the dynamical map. Well, it'll just be written as e to the L t1 plus t2, right? Just using the exponents add. So the dynamical map at a later time belongs to the same family as the dynamical maps of these intermediate times. So I'm not sure if that answers the question, but yeah, like it will commute with itself because it's time independent.
Yeah, I think this answers the question. We can go on.
Okay, yeah, so yeah, just using the definition of a dynamical map, if we differentiate V, we can attain an equation of motion for our reduced density matrix rho S by just differentiating V, and, you know, just in a very basic way, we can then show that a general equation of motion for our reduced density operator is given by what's in this blue box. So this is what's referred to as a Markovian quantum master equation, due to the fact that the dynamical map that satisfies this dynamical semigroup property, or is defined as a dynamical semigroup, describes a quantum Markov process. So the way that when I introduced the dynamical map, I introduced it as a way of leading us to simplify the general description of the dynamics of open quantum systems. So basically, from introducing the idea of a dynamical semigroup, we can then write down an equation of motion in a closed form equation of motion for of the reduced density of a matrix of our open system in this form. So what we can now do is say, is
the generator of semigroup unique?
No, and that's something that I'm just about to talk about.
Okay, great, thank you.
Yeah, so basically that was almost exactly what I was just about to talk about. So what you can ask is, okay, based on this, based on V defining a dynamical semigroup, what we can do is construct the most general form of this generator L for any for at least a large class of open systems. So I won't go through. So basically, you can give a proof, or a proof has been given of the most general form of this generator. I won't go through all of that, but I'll just basically sketch out some of the assumptions that go into this. So basically, in order to construct the most general form of this generator, what you assume is that the dimension of the Hilbert space of your open system S is of dimension n, so it's finite dimensional. And what you can do is you can introduce an orthonormal basis of operators for acting on the so-called Liouville space of your open system. So the Liouville space is kind of like the operators. The Liouville space is the set of bounded operators on our acting on our open system. So you can introduce an orthonormal basis of operators labeled Fi. So there are n. So for a open system of dimension n, there are n squared operators. There are n squared basis operators, and these form an orthonormal basis. So they basically satisfy the fact that they're in a product, which is defined in the following way. At the bottom, basically, is the Kronecker delta. So these are kind of just technical definitions that go into to proving the most general form of the or the construction of the most general form of the generator. But I won't go over this. These are just kind of details to keep in mind. Okay, I see there's another question. So should I take that?
The question is the cursive L represent the Lindblad operator? I think the answer is yes, and we can go on.
Yes. So yeah, that's on the next slide. Yes. So so what you can show, so using these ingredients, what you can prove is that using this dynamical semigroup condition is that what's called the first standard form of the generator is given as follows. So in the expression in this blue at the top, H is defined as a self-adjoint operator acting on our open system. So you can think of this as kind of a Hamiltonian, but in general, it's just any self-adjoint operator. And so that's contained in the first part of the expression. In the second part of this expression, we have well, I should say in the first part of the expression, you can see that this kind of describes a kind of unitary evolution because it's in the form of a commutator. And then in the second part of this expression, we kind of have a term which describes a non-unitary evolution. So you can think of this second term as arising due to the fact that the dynamics of our open system is non-unitary due to the influence of the environment. And this second term is represented in terms of these operators that I introduced, F. And yeah, I should say that these curly brackets define the anti-commutator. So square brackets are commutator and curly brackets are anti-commutator. And these coefficients Aij, these coefficients form or are the coefficients of a positive semi-definite matrix of dimension n squared by n squared. And so this defines the first standard form of the generator. So what you can do is, so you can see that the second term is in a non-diagonal form because it contains a sum over two indices I and j. So what you can do is you can diagonalize the second part of the expression by introducing a new set of operators ak, and these new operators ak are related to these operators f via unitary transformation. So these coefficients u, k, I define the coefficients of a unitary matrix, And what you can basically, so the reason that you relate these via a unitary transformation is that, well, these coefficients Aij are the coefficients of a positive semi-definite matrix, and in general, any positive semi-definite matrix can be diagonalized by a unitary transformation. So we basically choose this unitary transformation such that it diagonalizes this matrix, this A, and because this matrix A is positive semi-definite, then its eigenvalues, which are labeled gamma 1, gamma 2, all the way up to gamma n squared minus 1, its eigenvalues are, by construction, non-negative, so positive, and so either 0 or positive. Okay, so basically just substituting this expression, so this expression for Fi in terms of A into the above, we basically can then come up with a diagonal form of this generator. And this is, so the person said, or the person asked, is this the limit? Does this calligraphic L give the I'm not sure if they said Lindbladian or Lindblad operator, but basically this then gives you the diagonal form of the generator. So this is what's commonly referred to as the Lindblad form of a master equation. So yes, so you can see, so this proof that that the most general form of the generator of a dynamical semigroup can be written in this form was first given by Guarini, Kosakowski, and Schuderschein in 1976, and I think shortly thereafter it was also shown by Lindblad. So yes, this most general form of master equation is it's commonly referred to the Lindblad form of the master equation, but when you're writing papers, you have to be careful to give kind of credit to all the people that first gave this proof. So it's also referred to as in the long form as the Guarini, Kosakowski, Schuderschein, Lindblad form of the master equation, or in a shorter sense, just the GKSL form of the master equation, or GSKL form of the master equation. Okay, so just to kind of summarize, like basically what we've shown is that for a so I should just go back to this slide quickly. So we have a dynamical equation for our reduced density matrix rho S, which can be written in this form under the assumption that our dynamical map forms a dynamical semigroup. And this equation of, I should have mentioned, I'm not sure if I mentioned this earlier, I should have probably mentioned it if I didn't, but basically this equation of motion is what's commonly referred to as a master equation. So a master equation is basically just an equation of motion for the reduced density operator of an open system. And what we've basically proven is that the most general form of this master equation can be given in this diagonal form that's at the bottom of this slide in terms of these operators. So in terms of a self-adjoint operator H, and in terms of these other operators A and K, which are just operators pertaining to our open system. And this is also written in terms of these coefficients gamma of K. So these coefficients gamma of K can be what if I get enough time to talk about it later on, which I'm not sure, I just realized the time now actually, but when we go through a microscopic derivation of the master equation, you can show that these coefficients can be interpreted as transition rates between different states of our open system. Okay, so I think that's all I have to mention on this slide. And is there any questions about that? Or
so far there is no question.
Okay, I just realized the time, so I'm not sure if that's, I wanted to get through more material, but I'm not sure if I should carry on for a little bit more, or should I just stop?
I think, Graeme, this is probably a very nice moment to stop on a highlight of the theory of open quantum systems, and maybe we should give the participants the opportunity maybe to ask a few more questions. Yeah, no, thank you very much for sharing the highlight again. Yeah.
Yeah, so if there's anything to take away from this lecture, I would say that it's this result, or I should say that the master equation, well, the equation of motion for a reduced density operator, which describes a quantum Markov process, can be written in this form, and that the most general form of the generator L is given by the second expression on this slide. So basically,
there is a question.
Yeah, yeah.
And what is the relation between the semigroup and memorylessness of the bus?
Yeah, so that's quite I think you can answer that question on many levels. I'll answer it on, I'll give one answer, but I think there are potentially many answers to this. So basically, the dynamical semigroup property describes a memoryless process in the sense that, okay, well, I should say that firstly, you can use this dynamical semigroup property to show that that the equation of motion for the reduced density matrix of your system can be written in this form. Could be written in GKSL form, right? So what's given on the second slide. So basically, when you go through a microscopic derivation of a master equation, which was what I was going to move on to, but unfortunately we've run out of time. What you can show is that when you make a series of approximations and assumptions, which correspond to basically assuming that that the dynamics generated by the interaction between your system and environment gives a memoryless process at the level of your open system, you basically come up with a master equation of GKSL form, so of the form at the bottom of the slide. So the connection of the dynamical semigroup to memoryless processes, I would say, in the answer that I've given, is through the master equation, because you can basically, yeah, you can give a microscopic derivation of this master. So I've just given like a kind of mathematical kind of construction of the master equation, but what you can actually do is you can describe this you can derive this form of master equation microscopically. So you can start from you can go back to the Hamiltonian and then make a series of assumptions which basically assume things like that your bath contains no memory of, you know, that the interaction is basically gives rise to a memoryless process, and then you end up with a master equation of this form. So sorry, I think that was maybe a bit of a verbose answer, but
yeah, I think it's a wonderful answer. It becomes much more clear when you're going to demonstrate the microscopic derivation.
Yeah, yeah.
And so far there is no more questions.
Should we end, Graeme, maybe with a short preview of what you will share with us next week?
Yeah.
Just
so in
words to attract the participants again, like yeah.
Yeah. So in next week's lecture, what I will go on to talk about is the microscopic derivation. So the microscopic derivation of the Markovian quantum master equation. So the microscopic derivation of a master equation of this form, and what this basically involves is going back to let me just go up here. It involves going back to this part that I discussed towards the beginning, and then showing that by introducing like a general form of interaction Hamiltonian, that you can then basically make a series of assumptions regarding the system environment interaction, like, for example, assuming weak system environment coupling and assuming that the time evolution of your reduced system is memoryless. Then you basically end up with a master equation of GKSL form. So basically what I will do is connect the form of the master equation that I've given here to the actual derivation that you can perform microscopically.
Thank you, Graeme. That will be very interesting to see next week. Thank you very much. Yeah. Okay, if there are no more urgent questions, as usual, we will upload the video of the lecture in our YouTube channel, and I'm looking forward to see you all again next week. Yeah, and Graeme, thank you very much for the nice presentation. And Ilya, thank you very much for moderating the question. Thank you very much. Yeah. Okay, so have all a good afternoon, and please keep staying safe. Thank you. Bye-bye.
Okay, thank you. Bye.
Thank you. Bye-bye.